This video explains the introduction to the strand interaction diagram. So these lectures explain for the columns under various loading conditions. Now in the Australian standard AS360 on page number 159 clause 10.6.2 has given the load interaction diagram, where on the y-axis you have axial load and on the x-axis you have moment, and it has, let's say, point A, point B, point C and point D. It has various points given in this one, and it has given the clause where you can find those points. In the next video we will take the example to find those points. Now I like to explain some of the points here. So now point number A, which is the bending moment, is 0 here. This bending moment is 0 here, where you have axial load. This is the conditions when you have a pure axial load. You have a, let's say for these columns, if you have a x-axis and y-axis, your loading is applied in the middle. That will be the this point A, where you have 0 bending moment. Pure axial load going to the centroid of the column is this squash load. Now for this case, if I take the strain profile for these columns, for example, for this profile, this is the compressions and this one will be compression. So everything will be under compression condition. So this is a strain. Both steel and concrete will have a same strain value under these loading conditions. When I talk about point B, which is a decompression point, what does it happen? So when you have a eccentricity, when I apply the loading somewhere, let's say eccentric loading apply something outside of that point, will have a bending. So we have some bending moments, and as the bending moment increase, the axial load will increase. So this is point B, is a decompression point, where you have a compression strain 0.03 for a concrete, and you have a 0 tensile force. Now point C is divided into two sections. One is a balance nominal and another one is balance actual. Actually, when you have a 500 megapascal steel, when you calculate the strain, you have a 0.025. So that is point C. The Australian standard saying that 500 megapascals. Now, for example, if you want to design for high strain concrete 690 megapascals, for example, AS2327 for steel and composite columns, they allow now 690 megapascals. So if you want to use a 690 megapascal reinforcement, your yield strain is 0.035. so you have a yield strain of 0.035. so your point is balance actual. So you will get two different points when you have a concrete when you have a steel strain greater than 500 megapascal. If you have a steel strain 500 megapascal, then this point would be the 1 point balance actual, and balance normal is the 1 point at point C. And the pure bending moment is at point D, where you will have a strain profile here. This is actually neutral axis, where you have a perfect neutral axis. Half goes on the compression, half goes on the tension side of the strain. For here you will have also neutral axis. You have more portion of the compression and the less portion on the tension side. So these are the just general informations about the axial load moment diagrams. Now I have just drawn these figures as well here. Let's say you have these columns for the point number A, which is point number A here. When you are axial loading applying here, you have point A, you have pure compression. Everything is under compressions. Now when you increase the loading, like for example, if I have loading here, this is point A. Now if you increase the loading with the eccentricity, if you increase the eccentricity is 0 here, but when you increase the eccentricity, it goes under bending. So you have a point B, and you have bending moments in your axial load and bending moment in your columns. As you increase the eccentricity, so if you keep increasing the eccentricity, loading increase, your bending moment will be increased, because your bending moment would be load times eccentricity. So if your eccentricity is increased, your bending moment will be increased. So in that case, you will have this point C, and I explain you this point C. When you have 500 megapascals, you will have a same strain profile, but if you have reinforcement greater than 500 megapascals, you will have a yield point somewhere here, which is not same as 0.025. so you will have two different points at point C. And at point D, which is pure bending moment, you have 0 axial force, you will have perfect balance, and this is your neutral axis. So generally we use the software to do the structure analysis software or coding to do this one, because finding the neutral axis for equilibrium is a quite challenging process. But for design purpose, we're going to use the Australian standards, where we're going to look at the plotting of this axial load moment interaction diagram. Thank you very much.